Reality itself is a collection of unsolved puzzles. 26 profound riddles are woven into the fabric of the cosmos, and scientists are in a race to decode them. These are not abstract curiosities. They are the very mysteries that define the limits of our understanding, from the ghostly presence of dark matter to the bizarre paradoxes of quantum mechanics. Unlocking these secrets could revolutionize technology and redefine our place in the universe. By the end of this journey, you will have a clear view of the most compelling questions at the frontier of science. What if the laws of physics are not what they seem? Why does the universe appear perfectly tuned for life? We are about to explore the riddles that challenge everything we think we know. What part of reality would you most like to see explained? Galaxies should fly apart. The immense speed at which stars orbit their centers creates a centrifugal force so powerful that the visible matter, the stars and gas we can see, simply does not provide enough gravity to hold them together. And yet, they do not tear themselves to pieces. They are held fast by an unseen hand, a ghostly presence that exerts a gravitational pull without emitting or absorbing a single photon of light. This is the first and perhaps most profound riddle woven into reality, the mystery of dark matter. It is the invisible scaffolding of the cosmos, accounting for roughly 27% of everything that exists. We know it is there only because we can see its gravitational signature, the way it bends the fabric of space-time and dictates the motion of galaxies. The pioneering astronomer Vera Rubin, whose meticulous work first confirmed this galactic anomaly, put it perfectly when she said we are seeing only the tip of the iceberg. For decades, scientists have hunted for what this hidden substance could possibly be. Leading candidates have included theoretical particles with names like WIMP, or weakly interacting massive particles, and actions, which are unimaginably light and elusive. Countless experiments deep underground, shielded from cosmic interference, have sought to catch a single one of these particles in the act of interaction. So far, every detector has come up empty. The evidence for dark matter's influence, however, is everywhere. Look at the Bullet Cluster, a spectacular collision of two galaxy clusters. During the crash, the hot gas from each cluster, the normal matter, slowed down and piled up in the center. But something else kept right on going. By mapping the gravitational lensing, the way background light is bent, astronomers could see that the bulk of the mass, the dark matter, had sailed straight through the collision unaffected, separated completely from the visible stuff. This is perhaps the clearest proof we have that dark matter is real and distinct. It is the hidden architect that drew matter together after the Big Bang, seeding the vast cosmic web of galaxies we see today. Its gravitational pull will ultimately determine the fate of the entire universe, so we are left with a haunting question. After all this time and all this effort, what if we are wrong? What if dark matter is not a sea of unknown particles but a sign that our understanding of gravity itself is incomplete on the largest scales? It is a possibility that forces us to confront a humbling thought, that the fundamental rules we believe govern reality might only be a partial truth. This invisible enigma is the first thread we pull, and it is connected to an expansion that defies all logic. But if dark matter is the hidden hand holding the cosmos together, then what is the force relentlessly and violently tearing it all apart? This is the second riddle, the mystery of dark energy. The universe is not merely expanding, it is accelerating, with galaxies rushing away from each other at a pace that increases with every passing moment. This startling discovery, made in the late 1990s by two independent teams observing distant supernova, completely upended cosmology. The expected finding was that the universe's expansion should be slowing down, gradually decelerating under the collective pull of gravity from all the matter within it. Instead, they found the opposite. a runaway expansion getting faster and faster as if some unseen repulsive force was overwhelming gravity itself. This mysterious driver was named dark energy, and it constitutes a staggering 68% of the entire universe. Cosmologist Adam Rees, who shared a Nobel Prize for this landmark discovery, called dark energy the most profound mystery in all of science. What could possibly be causing this? The leading and most perplexing idea is Einstein's cosmological constant, a term he originally inserted into his equations of general relativity to force a static universe, a move he later called his biggest blunder. It represents a constant energy density smoothly filling the vacuum of space itself. The problem is that when physicists try to calculate the expected value of this vacuum energy using quantum mechanics, their result is off by a factor of 1 followed by 120 zeros, a number so colossal it is arguably the worst theoretical prediction in the history of science. Alternative theories propose a dynamic field, nicknamed quintessence, that changes over time, yet none of these ideas fully explain the nature of this dominant cosmic force. Its implications, however, are terrifyingly clear. Dark energy dictates the ultimate fate of everything. If it continues to strengthen, it could lead to a big freeze, where the universe expands into a cold, dark, and empty void, with galaxies pushed so far apart that the night sky in the far future would be utterly black. Or, in a more violent scenario called the Big Rip, the accelerating expansion would eventually overcome all forces, shredding galaxies, solar systems, planets, and even atoms themselves in a final, catastrophic end. Precision measurements from observatories like the Planck satellite, which maps the faint afterglow of the Big Bang known as the cosmic microwave background, continue to constrain these models, but the enigma only deepens. Could dark energy be a sign of extra dimensions leaking into our own? Or perhaps the most glaring evidence that Einstein's theory of gravity, while brilliant, is ultimately incomplete on the grandest scales? This force pushes us to question the very fabric of spacetime, a mystery that is utterly dominant yet completely invisible, and it forces us to ask if the answers lie not in the vast cosmic expanse, but in the bizarre rules that govern the smallest pieces of reality. These two fundamental theories, one for the immense and one for the infinitesimal, are both spectacularly successful in their own domains, yet they speak completely different mathematical languages and obey contradictory rules. This is the third great riddle, the quest for a theory of quantum gravity, a single framework that can describe all of reality. General relativity is a classical theory, painting a smooth, continuous picture of spacetime as a flexible fabric warped by mass and energy. Quantum mechanics, on the other hand, reveals a subatomic world that is granular, probabilistic, and inherently fuzzy. When we try to apply both theories to the same extreme environment, like the center of a black hole or the very first moment of the Big Bang, the mathematics completely breaks down, producing nonsensical infinities known as singularities. This tells us that our understanding is incomplete. As physicist Brian Greene has noted, the universe is built on a foundation that we have not yet fully uncovered. For decades, the brightest minds have pursued potential paths to unification. String theory suggests that the fundamental constituents of reality are not point-like particles but incredibly tiny, vibrating loops of energy. The different vibrations of these strings would give rise to all the particles and forces we observe, potentially including gravity. However, this elegant idea requires extra dimensions of space beyond the three we experience, dimensions that are curled up and hidden from view. Another compelling approach is loop quantum gravity, which proposes that spacetime itself is not smooth, but is woven from a network of discrete, finite loops, much like a fabric is woven from individual threads. This would eliminate the problematic singularities, meaning there was no point of infinite density at the beginning of the universe, but rather a big bounce from a previous cosmic phase. The greatest challenge for all these theories is a complete lack of experimental evidence. We simply lack the technology to probe such incredibly small scales and high energies directly. Yet, the conflict plays out dramatically in a thought experiment known as the black hole information paradox. According to general relativity, if you throw an object into a black hole, it is lost forever behind the event horizon, its information seemingly erased from the universe. But quantum mechanics insists that information can never be truly destroyed. So, which law of physics gives way? Does the information slowly leak out as Hawking radiation? Or is it preserved on the surface of the event horizon like a cosmic hologram? This paradox forces us to ask a truly profound question. What if spacetime itself is not fundamental? What if it emerges from something deeper, a more basic building block of reality that we have not yet even conceived? Unifying these two pillars is not just an academic exercise. It is a necessary step to comprehend the origin of our universe and its most extreme phenomena. It challenges us to rethink the nature of existence itself, suggesting that the smooth, continuous stage upon which we live our lives may be an illusion. And this rethinking must include the most familiar and yet most mysterious dimension of all. Yet we all feel its relentless, one-way flow. The arrow of time is perhaps the most intimate riddle we experience, a universal truth that defines our existence yet defies easy explanation. Why does time move only forward, from a fixed past to an uncertain future, when the fundamental laws of physics, from Newton to quantum mechanics, work perfectly well in reverse? If you were to watch a film of two billiard balls colliding and ricocheting apart, then watch that same film played backward, both sequences would look entirely plausible. The physics is symmetric. So why does our reality only play the film in one direction? The answer, physicists believe, lies not in the laws themselves, but in the arrangement of the universe. It is a story of probability and initial conditions, centered on a concept called entropy, which is a measure of disorder or randomness. The second law of thermodynamics states that the total entropy of an isolated system always increases over time. Things move from order to disorder, from a neat stack of papers to a messy desk, from a hot cup of coffee to one that is room temperature. This ever-increasing entropy gives us the arrow of time. We remember the past because it was a state of lower entropy, and we anticipate a future of higher entropy. But this only pushes the mystery further back. Why was the entropy of the universe so incredibly low in the first place? The Big Bang represents a moment of unimaginably low entropy, a state of exquisite order that has been unraveling and dispersing for nearly 14 billion years. Physicist Sean Carroll has pointed out that this is the real puzzle. We need to explain why the early universe was in such a special, ordered state. Some theories suggest that our universe is just one bubble in a vast multiverse, and we simply find ourselves in a region where the initial conditions allowed for the formation of stars, planets, and life. Others delve into quantum mechanics, where the process of decoherence, the point at which quantum possibilities collapse into a single reality, might create the perception of a flowing time. This leads to a profound and almost unsettling thought. Could time itself be an emergent property, not a fundamental feature of the universe? Is our experience of past, present, and future merely a persistent illusion generated by our consciousness as it processes a world moving from order to disorder? What if the underlying reality is timeless, a static block where all moments exist simultaneously, and our journey through it is just a trick of the mind? This riddle forces us to question the very nature of our experience, challenging the most basic feeling we have about reality, and it connects directly to another cosmic mystery, one that asks why the conditions for our journey were set so perfectly from the very beginning. The universe should not exist, not as we know it and certainly not with us in it. This is the fifth riddle, the mystery of cosmic fine-tuning. All it would take is a tiny, almost imperceptible tweak to any of the fundamental constants that govern reality, and everything would vanish. If the force of gravity were even slightly stronger, the universe would have collapsed back on itself immediately after the Big Bang. If it were slightly weaker, matter would never have clumped together to form stars and galaxies. Stars themselves are impossibly precise engines. The process that creates carbon, the fundamental building block of life as we know it, relies on a breathtakingly exact resonance level within stars. If that resonance were off by even a fraction of a percent, the elements that make up our planet and our bodies would never have been forged in stellar furnaces. The cosmological constant, the value that governs the strength of dark energy, is perhaps the most startling example. For the universe to be habitable, this number had to be almost zero, but not quite. If it were any larger, the universe would have blown itself apart before the first star could form. If it were any smaller, it would have collapsed. The odds of all these dials being set to their exact, life-permitting values by pure chance are astronomically small, like a whirlwind assembling a perfect watch from a pile of scattered parts. This profound balance forces a difficult question. Are we the beneficiaries of unimaginably good luck, or is there a deeper principle at work? Cosmologist Martin Rees has championed one compelling answer: the multiverse. In this view, our universe is just one bubble in a vast, perhaps infinite, cosmic foam. Each of these universes has its own random set of physical laws and constants. We simply find ourselves in one of the rare, Goldilocks universes where the conditions are just right for life to emerge. This is known as the Anthropic Principle, the idea that our existence as observers selects for the very conditions we observe. String theory lends a mathematical hand to this idea with its concept of the landscape, a colossal number of possible vacuum states, each corresponding to a universe with different laws. Yet for many, this feels like an unsatisfying retreat from explanation. Is the multiverse a profound scientific prediction, or is it merely a convenient way to explain away a miracle? Could fine-tuning instead be evidence of some form of design, or perhaps a sign that these constants are not free parameters, but are locked together by a deeper, undiscovered theory of everything? The fine-tuning problem does not provide easy answers, but it does something perhaps more important. It forces us to confront the sheer unlikeliness of our existence and to ask what it truly means that we are here at all, in a universe that seems to have been expecting us. This leads to a riddle that is even closer to home, one that asks not about the cosmos, but about the very nature of the mind that observes it. But if the universe is so perfectly tuned for life, then what is life itself? We arrive at the sixth riddle, a mystery that is not written in the distant cosmos but is happening right now, behind your eyes. It is the hard problem of consciousness. We can map the brain in exquisite detail, tracing the firing of neurons and the flow of chemicals. Science has solved what philosopher David Chalmers calls the easy problems, explaining functions like attention, memory, and the control of behavior. But none of this explains the most immediate fact of your existence, the raw, subjective experience of it all. Why do we have an inner life? Why does the processing of a specific wavelength of light by your visual cortex result in the rich, private sensation of the color red? This subjective quality of experience is known as qualia, and it is the central mystery. Neuroscientist Christoph Koch put it perfectly when he said consciousness is the central fact of our existence, yet we do not understand it. We can locate the neural correlates of consciousness, the specific brain activities that coincide with experience, in experiments like binocular rivalry, where each eye is shown a different image. The brain does not blend them. Instead, your conscious perception flips back and forth between the two, allowing scientists to see which parts of the brain activate with that shift in subjective awareness. But correlation is not explanation. Knowing which circuits light up does not tell us why they light up with feeling. To bridge this gap, radical theories have emerged. Panpsychism proposes that consciousness is not a product of complex biology, but a fundamental property of the universe, much like mass or charge. In this view, even an electron might possess a tiny spark of experience, and complex systems like our brains simply amplify it. Another compelling idea is integrated information theory, which suggests that consciousness is the capacity of a system to integrate information. The more interconnected and differentiated a system is, the richer its conscious experience. This theory even provides a metric, called phi, to theoretically measure the level of consciousness in any system, from a human to a computer chip. Yet none of these ideas are proven. They all stumble before the same profound question: how does the objective machinery of the brain generate the subjective movie of the mind? Could it be that consciousness is not generated at all, but is a basic feature of reality, woven into the fabric of spacetime itself? This riddle blurs the line between science and philosophy, forcing us to wonder if the mind is merely a passive observer of the universe, or if consciousness itself plays some active role in shaping reality. And if consciousness is so deeply fundamental, it makes the emergence of life, the vessel that seems to carry it, an equally profound puzzle. Earth 4 billion years ago was a violent and alien world, a molten rock under constant bombardment, with an atmosphere poisonous to life as we know it. And on this seemingly inhospitable planet, something impossible happened. Inanimate matter, a random collection of chemicals, somehow crossed a fundamental threshold. It became a self-replicating system, taking the first tentative step toward becoming alive. This is the seventh riddle, the mystery of abiogenesis, the origin of life from non-life. How did inert chemistry give birth to biology? The gap between a warm little pond full of organic molecules and even the simplest living cell is a chasm that science has yet to bridge. Nobel laureate Jacques Chastak, who has dedicated his career to building a synthetic cell from scratch, admits we are getting closer, but the origin of life remains one of science's great puzzles. The most promising hypothesis is the RNA world idea. RNA is a remarkable molecule. It can store genetic information like DNA, and it can catalyze chemical reactions like a protein. The theory suggests that before the modern system of DNA and proteins, a simpler world existed where self-replicating RNA molecules were the first pioneers of life. Scientists have shown that RNA can indeed form spontaneously from simpler precursors and even evolve under the right conditions. Other theories point to deep-sea hydrothermal vents. These porous, rocky structures on the ocean floor provide a natural chemistry set, with mineral catalysts, a steady energy source from geothermal heat, and protective compartments that could have corralled the first molecules of life. Then there is the more speculative idea of panspermia, which suggests that the building blocks of life, or even primitive life itself, could have been delivered to Earth by comets or asteroids. But this only pushes the mystery elsewhere, to some other world. The challenges are immense. The famous Miller-Urey experiment in the 1950s showed that the basic building blocks of life, amino acids, could be formed easily from a simulated early Earth atmosphere. But going from a handful of amino acids to a complex, self-replicating, membrane-bound cell is a leap of staggering complexity. How did these molecules assemble without modern cellular machinery to guide them? How did they develop a genetic code, a way to copy themselves, and a membrane to separate themselves from the chaotic outside world? Every proposed pathway has a missing link. This forces a profound and reflective question: is life a cosmic imperative? Given the right conditions and enough time, is chemistry almost destined to become biology, a natural outcome of the universe's laws? Or is life an astronomically rare fluke, the result of a series of chemical accidents so unlikely that we might truly be alone in the vastness of space? The answer to this riddle does not just define our past. It defines our future, shaping everything about how we search for our place in the cosmos and for answers to the ultimate question. Are we the universe's only children? The profound silence of the cosmos is its own unsettling riddle. Our telescopes reveal a universe teeming with promise, with billions of Earth-like planets orbiting in the habitable zones of their stars. The numbers from the Drake equation, a framework for estimating the number of communicative civilizations, suggest the galaxy should be buzzing with activity. And yet, when we listen, we hear only a vast, unnerving quiet. This contradiction is the Fermi paradox, named for physicist Enrico Fermi, who, during a casual conversation in 1950, posed the deceptively simple question, where is everybody? If life is a natural cosmic process, the galaxy should have been colonized many times over by now. The silence suggests something is terribly wrong with our assumptions. Astronomer Jill Tarter, a pioneer in the search for extraterrestrial intelligence, offers a crucial perspective, reminding us that absence of evidence is not evidence of absence. Our search has been incredibly limited, like scooping a single glass of water from the ocean and concluding there are no whales. Projects like SETI have scanned only a tiny fraction of stars and frequencies, and for a mere cosmic instant. Yet the paradox persists, forcing us to consider sobering possibilities. Perhaps life itself is extraordinarily rare, a series of perfect accidents that may not have happened anywhere else. Or perhaps life is common, but intelligence is not. Maybe the evolutionary path to a technological civilization is littered with traps. This idea is crystallized in the Great Filter Hypothesis, which proposes there is at least one insurmountable barrier that prevents life from progressing to the stars. The terrifying question is whether that filter is behind us, a step we miraculously passed, like the emergence of complex cells, or if it still lies ahead of us, a fate like nuclear war or environmental collapse that dooms all advanced civilizations. Other solutions are even more mind-bending. The zoo theory suggests we live in a kind of galactic wildlife preserve, with advanced civilizations observing us but adhering to a strict non-interference policy. Or perhaps interstellar travel is impossibly difficult, or all advanced intelligence eventually uploads itself into immersive virtual realities, losing all interest in the outside physical universe. There are fleeting moments of hope that break the silence, like the famous WOW signal detected in 1977. It was a strong, narrow-band radio signal that matched the expected signature of an artificial transmission from deep space. It lasted for 72 seconds and was never heard again, despite repeated searches. It remains the best candidate we have, a single, enigmatic shout in the dark. The Fermi paradox ultimately holds up a mirror to humanity. It forces us to ask not only where the others are, but what our own future might hold. Are we the first, the last, or the only ones to reach this point? The answer may lie not in the stars, but in the bizarre rules that govern the universe at its most fundamental level, where particles defy all common sense. A single electron fired at a barrier with two slits does not choose one path or the other. It behaves as if it passes through both openings simultaneously, creating a telltale pattern of light and dark bands on the detector screen behind it, an interference pattern that is the unmistakable signature of a wave. But then, if you place a detector at one of the slits to see which path the electron actually takes, the behavior changes instantly. The electron is caught, acting like a single, localized particle, and the beautiful wave pattern vanishes. This is the ninth riddle, the bewildering wave-particle duality. The most fundamental constituents of our universe, from photons of light to atoms and even large molecules, possess this schizophrenic nature. They are both discrete particles and spread-out waves, and they switch between these identities based solely on whether we are watching. Physicist Richard Feynman famously quipped that this double-slit experiment contains the central mystery of quantum mechanics, a mystery he believed nobody truly understands. This bizarre behavior forces a radical reinterpretation of reality. The Copenhagen interpretation, championed by Niels Bohr, states that particles do not have definite properties like position or momentum until the moment they are measured. Before observation, they exist in a fuzzy cloud of all possible states, a superposition described by a mathematical wave function. The act of measurement itself, the interaction with a conscious observer or a macroscopic device, is what collapses this wave function, forcing the particle to pick a single, definite reality. This introduces probability as a fundamental feature of the universe, not a sign of our ignorance. We cannot predict where an electron will land on the detector screen, only the odds of where it might appear. This idea that the observer plays a role in creating reality is deeply unsettling, but there are alternatives. Pilot wave theory, for instance, suggests that particles are indeed real, point-like objects that are guided by a real physical wave. This creates a deterministic universe where the weirdness is hidden in the complexity of the wave's motion. Yet for most physicists, the Copenhagen interpretation remains the standard view, partly because of a process called quantum decoherence. This explains how the fragile superposition of a single particle is rapidly destroyed by interactions with its environment, making it appear to collapse into a single state without the need for a conscious observer. So where does this leave us? Is the universe fundamentally probabilistic, a game of chance at its very core? Or is it deterministic, with the dice loaded by hidden variables we have yet to discover? The wave-particle duality forces us to confront the limits of classical intuition and accept that the solid, predictable world we experience is an emergent illusion, built upon a foundation of profound and inherent uncertainty. And if a single particle can be in two places at once, what happens when two particles become inextricably linked, instantly influencing each other across any distance? Two particles born from the same quantum event can be flung to opposite ends of the galaxy. Yet, the moment you measure the spin of one, its distant partner instantly snaps into a perfectly correlated state, as if they share a single existence. This is quantum entanglement, the 10th riddle, a phenomenon so bizarre that even Einstein rejected it, deriding it as spooky action at a distance. He believed it revealed a flaw in quantum theory, not a feature of reality. He, along with colleagues Podolsky and Rosen, formulated the EPR paradox, arguing that if quantum mechanics were correct, it would require this impossible, instantaneous communication, thereby violating the cosmic speed limit set by the speed of light. For decades, it remained a philosophical debate. Then came physicist Alain Aspect and his groundbreaking experiments in the 1980s. He tested a mathematical theorem devised by John Bell, a set of inequalities that could distinguish between a universe with hidden variables, as Einstein hoped for, and one with true spooky action. Aspect's results were clear and revolutionary. The inequalities were violated. Einstein was wrong. The particles were connected in a way that defied any classical explanation of locality, the idea that objects are only influenced by their immediate surroundings. This non-locality is now an established fact of nature. But how can two things communicate faster than light? The leading interpretations offer wildly different answers. The Copenhagen view suggests there is no communication at all. The two particles are not separate entities but parts of a single, indivisible quantum system. Measuring one part simply reveals a property of the whole. The many worlds interpretation proposes that the act of measurement splits reality. When you measure the first particle, the universe branches. In one branch, you see spin up, and in the other, spin down. The second particle is simply in the correlated branch of the same universal wave function. And pilot wave theory argues that the particles are indeed guided by a non-local wave, connecting them across space in a way that is hidden from our view. Regardless of the explanation, the practical implications are staggering. This spooky action is the engine of the coming quantum revolution. Quantum computers rely on entangled qubits to perform calculations that would take classical supercomputers longer than the age of the universe. Quantum teleportation, which is not the Star Trek kind, uses entanglement to transfer the quantum state of a particle from one location to another without physically moving it. And perhaps most tangibly, entangled photons are already being used to create perfectly secure communication networks. Any attempt to eavesdrop on the line would break the delicate entanglement, immediately alerting the users to the intrusion. This forces a deeply philosophical question. Does this instantaneous link mean the universe is fundamentally unified, a single, interconnected whole where separation is merely an illusion? Are we looking at a reality where, at the most basic level, everything is touching everything else? This profound connectedness hints at a deeper layer of existence, one that might even be powered by the seemingly empty space that fills the void between all things. The vacuum of space is not empty. Quantum physics tells us that what we perceive as nothing is actually a seething, bubbling sea of virtual particles, constantly flashing into and out of existence. This quantum foam should be bursting with an immense energy, a pressure that would violently warp the fabric of space-time. And yet, when we look at the universe, we see something profoundly different. The energy of empty space is almost zero, a whisper so faint that it allows galaxies to form and the cosmos to evolve. The discrepancy between the theoretical prediction and the observed reality is the most staggering failure in all of science, a miscalculation of 1 followed by 120 zeros. This is the 11th riddle, the cosmological constant problem, and it cuts to the very heart of our understanding of nothingness. The great physicist Steven Weinberg called it the most striking problem in contemporary fundamental physics. The vacuum energy, which we also call the cosmological constant, is the very engine of dark energy, driving the accelerating expansion of the universe. But why is its value so perfectly fine-tuned to be almost nothing? If it were just a little bit larger, the repulsive force would have been so powerful that it would have blown the universe apart before a single star could ever ignite. The most promising theoretical fix is a concept called supersymmetry, a beautiful idea that posits every known particle has a hidden superpartner. This symmetry would perfectly cancel out the vacuum energy, bringing the theoretical calculation down to zero. The problem is, we have not found a single one of these superpartners in our most powerful particle colliders. This failure has led many to a radical conclusion, that the cosmological constant is not a puzzle to be solved by one equation, but a selection effect. In a vast multiverse, every possible value of this constant exists in some bubble universe. We simply find ourselves in one of the rare universes where the value is small enough to allow for our existence. This is the anthropic principle in its most extreme form. It forces a difficult choice. Is the value of nothing a random, lucky draw in a cosmic lottery? Or is it the most glaring sign that we are missing a fundamental piece of physics, a deeper theory that will finally explain why the universe is built this way? This riddle of emptiness leads us directly to the most extreme environments the universe has to offer, places where the very concepts of space and time break down completely. At the very edge of a black hole, where gravity is so strong that not even light can escape, lies a paradox that threatens to unravel the foundations of physics. What happens to the information that describes an object when it falls in? According to the pristine rules of quantum mechanics, information can never be truly destroyed. It might be scrambled, but it must, in principle, be recoverable. This is a sacred principle called unitarity. Yet, general relativity paints a very different picture. It says that anything crossing the event horizon is lost forever, crushed into the singularity at the center. The object's information, the specific arrangement of its particles that made it unique, is seemingly erased from our universe. This is the black hole information paradox, and it represents a direct conflict between our two most powerful theories of reality. The problem was sharpened by Stephen Hawking's own discovery. He realized that black holes are not completely black. Due to quantum effects near the event horizon, they slowly radiate energy, a faint glow now known as Hawking radiation. This radiation causes the black hole to gradually lose mass and eventually evaporate completely. But here is the catch. Hawking radiation is purely thermal, random noise. It appears to carry no information about what fell in. So if the black hole vanishes, what happens to all that information it consumed? Is it truly lost, violating a core tenet of quantum physics? Hawking himself initially believed it was, famously making a bet that information was destroyed. He later changed his mind, conceding that the information must somehow be preserved and encoded in the radiation. But the mechanism for this escape remains one of the greatest unsolved problems in theoretical physics. How can the details of a burned book be reconstructed from its ashes? To resolve this, physicists have proposed some truly mind-bending ideas. The holographic principle suggests that all the information about everything within a black hole's volume is actually encoded on its two-dimensional surface, the event horizon, like a cosmic fingerprint. The three-dimensional interior is a projection of this data, much like a hologram. This idea is supported by the AD-S/CFT correspondence, a profound mathematical duality that shows a theory of gravity in a volume is equivalent to a quantum field theory on its boundary. Another radical proposal is the black hole firewall. If information is to escape, the event horizon might not be the smooth, uneventful space Einstein predicted. Instead, it could be a blazing wall of high-energy particles that would instantly incinerate any object falling in, preserving information at the cost of the equivalence principle, a cornerstone of general relativity. The key to testing these ideas may lie in the page curve, a theoretical graph that charts how information leaks out of an evaporating black hole. Recent advances in quantum gravity suggest that after the black hole has evaporated halfway, the radiation suddenly begins to carry away the hidden information. Figuring out the precise shape of this curve is a major goal for theorists. This paradox forces a profound question. Are black holes not cosmic dead ends, but the ultimate cryptographic devices, holding the key to a deeper union of quantum mechanics and gravity? Their mysterious horizons might be where the true, holographic nature of our universe is written, a code we are only beginning to crack. And this idea that reality might be a projection leads directly to the theory that the entire cosmos began with a burst of expansion so violent it defies comprehension. The universe expanded faster than the speed of light in its first fleeting moments. To resolve two profound puzzles, the horizon problem and the flatness problem, cosmologists proposed a period of hyper-accelerated expansion called inflation. The horizon problem asks why the universe looks the same in all directions. Regions on opposite sides of the cosmos are so far apart that light has not had enough time to travel between them, meaning they could never have been in contact to even out their temperature. And yet, the ancient afterglow of the Big Bang, the cosmic microwave background, is almost perfectly uniform. The flatness problem is just as puzzling. The density of the universe appears to be exquisitely fine-tuned to a critical value, balancing on a knife edge between collapsing back on itself or flying apart into nothingness. Any tiny deviation from this perfect flatness in the early universe would have been amplified over billions of years into a cosmos that is either impossibly curved or empty. Our universe is not. Inflation solves both riddles at once, by stretching space itself by a factor of at least 10 to the 78th power in a fraction of a second. It took a tiny, homogeneous patch of the primordial universe and blew it up to become everything we can see, ensuring it was the same temperature everywhere. This violent stretching also forced the geometry of the universe toward perfect flatness, just as inflating a balloon makes its surface appear flatter and flatter. Cosmologist Alan Guth first proposed this idea, recognizing it as a spectacularly elegant fix, but it immediately raised a deeper question: what could possibly possess space to behave in such a fantastically violent way? The hypothesized answer is a strange energy field called the inflaton. In this theory, the inflaton field temporarily got stuck in a state of false vacuum, a high-energy configuration that imbued empty space with a tremendous repulsive gravity, driving the exponential expansion. Eventually, this field decayed, releasing its pent-up energy in a firestorm that reheated the universe, filling it with the hot plasma of the Big Bang. The problem is, we have no idea what the inflaton field actually is. It is a complete placeholder, a name for whatever unknown physics powered the engine of creation. We search for its fingerprints in the oldest light we can see. The theory predicts that quantum fluctuations in the inflaton field would have been stretched to cosmic size, creating tiny density variations that eventually seeded the formation of all the galaxies and clusters we see today. It also predicts that inflation would have generated ripples in spacetime itself, primordial gravitational waves, which would leave a faint, swirling pattern called B-mode polarization in the cosmic microwave background. Finding this pattern would be a smoking gun for inflation. But despite decades of searching with increasingly sensitive telescopes, this definitive signal remains elusive. The models for inflation are numerous and varied. Chaotic inflation suggests it can start anywhere from a random quantum fluctuation. Eternal inflation proposes that once started, inflation never truly stops overall, but instead continues in some regions, giving birth to an infinite multiverse of bubble universes, each with its own laws of physics. This leads directly to the measure problem, a profound mathematical headache. In an infinite multiverse, everything that can happen does happen, an infinite number of times. How do we then calculate the probability of anything, including our own existence? The Planck satellite has provided stunningly precise maps of the cosmic microwave background, and its data generally supports the broad idea of an inflationary beginning. But it has not been able to distinguish between the many competing models. We are left with a chillingly beautiful possibility. The entire observable universe, with its hundreds of billions of galaxies, may be just an infinitesimal speck within a much larger, eternally inflating meta-universe, a single bubble in a cosmic foam that has no end. This forces us to ask a haunting question. If inflation did happen, what kicked it off, and more mysteriously, what made it stop? The mechanism that began and ended the very birth of spacetime remains one of the greatest voids in our knowledge. And this creation event left behind another, equally baffling asymmetry, one that determined the very existence of matter. Every particle of matter we see has a hidden twin, a perfect mirror image with opposite charge. This is antimatter. According to our best theories, the Big Bang should have created matter and antimatter in absolutely equal amounts. And in that perfect symmetry lies a cosmic death sentence, for when matter and antimatter meet, they annihilate each other in a flash of pure energy. The entire universe should have vanished in a grand flash of mutual destruction moments after it was born. Yet here we are, in a cosmos made almost entirely of matter. This profound imbalance is the 14th riddle, the baryon asymmetry problem. For every billion particles of antimatter created in the early universe, there were 1,000,001 particles of matter. That 1 part in a billion is all that survived the great annihilation to form every galaxy, star, and planet we see. Without this tiny, inexplicable bias, our universe would be empty, a vast sea of radiation with no structure and no one to observe it. The Russian physicist Andrei Sakharov laid out the three necessary conditions to create this asymmetry. The universe had to be out of thermal equilibrium. It had to allow for processes that violated both charge and parity symmetry, known as CP violation, and it had to allow for interactions that violated baryon number, meaning the total amount of matter could change. The standard model of particle physics does contain a small amount of CP violation, which we have observed in the behavior of quarks, but it is far, far too weak to account for the overwhelming dominance of matter we see in the cosmos. It is like trying to explain a mountain with a single grain of sand. This glaring insufficiency is our clearest sign that new physics must be waiting to be discovered. Scientists are hunting for it in colossal machines like the Large Hadron Collider at CERN. They are studying the subtle differences between the behavior of matter and antimatter versions of particles like beauty quarks, searching for any deviation that could be the fingerprint of a much stronger violation. Another compelling idea is leptogenesis. This theory suggests that the initial asymmetry actually began not with quarks, but with neutrinos. Heavy, theoretical right-handed neutrinos could have decayed in the early universe, producing a slight excess of matter over antimatter in the lepton family. This lepton asymmetry could then have been converted into the baryon asymmetry we see today through a process called Sphaleron transitions, which are allowed in the standard model at extremely high energies. But these are all theoretical possibilities. We have not yet caught the culprit in the act. This leads to a tantalizing, almost science fiction question. If the asymmetry is not absolute, could there be entire domains of the universe, regions beyond our observable horizon, that are made predominantly of antimatter? Could antimatter stars and galaxies exist somewhere out there? Most physicists consider this unlikely, as any boundary between a matter region and an antimatter region would be a zone of constant, violent annihilation, lighting up the sky with gamma rays we do not see. The silence of our telescopes suggests the asymmetry is universal. This riddle forces us to confront a universe that is fundamentally lopsided, a place where the perfect symmetries we cherish in our equations are broken in reality. Our very existence is proof that the cosmos prefers one hand over the other, and we are left to wonder why. This fundamental bias toward matter is written into the fabric of everything, yet its origin remains one of creation's deepest secrets, pushing us to question the very meaning of symmetry as we probe the moment of observation itself. A quantum particle can spin both clockwise and counterclockwise at the same time, existing in a blur of all possible states. Yet the moment we look, this shimmering potential vanishes, collapsing into a single, definite reality. This sudden transition is the 15th riddle, the measurement problem, and it asks a deceptively simple question. What counts as a measurement? At its heart is the wave function, a mathematical description that encapsulates all the possibilities for a particle. According to the quantum rules, this wave function evolves smoothly and predictably until the instant it is observed, when it seems to break, collapsing to one outcome. But the theory itself provides no mechanism for this collapse. It is the biggest hole in our understanding of quantum mechanics. Physicist John Bell captured the absurdity perfectly when he asked if the wave function was just waiting to jump when somebody looked. The various interpretations of quantum mechanics are all attempts to answer this question, and they paint wildly different pictures of reality. The classic Copenhagen interpretation states that the act of measurement by a classical apparatus, or perhaps even a conscious observer, causes the collapse. This makes observation a magical, privileged process that stands outside the laws of physics. The many worlds interpretation offers a dramatic alternative. It says the wave function never collapses. Instead, the universe splits at every quantum decision. In one branch, you see the particle spin up. In another, an identical version of you sees it spin down. There is no single outcome, only an ever-branching multiverse of possibilities. Then there are objective collapse theories, which propose that collapse is a real physical process that happens spontaneously when a system becomes too large or complex. Experiments have pushed these ideas to their limits. The quantum eraser experiment is particularly mind-bending. It shows that you can change the past behavior of a particle, making it act like a wave or a particle, by making a choice about how to measure it in the present. This delayed choice seems to erase the previous history, suggesting that reality is not fixed until it is observed. This leads to the unsettling Wigner's friend thought experiment. Imagine a physicist, Wigner, outside a sealed lab. His friend inside measures a quantum particle and sees a definite result. But for Wigner, who has not yet looked, the entire lab, including his friend, is still in a superposition of states. Who is right? When does the collapse actually occur? This pushes the idea that consciousness itself might be the trigger, a notion that makes many physicists deeply uncomfortable because it places the mind outside of physical law. Some have tried to sidestep the issue entirely with quantum Bayesianism, which argues that the wave function does not represent reality, but only our personal beliefs and uncertainties about it. The collapse is just us updating our information, so we are left with a question that is as much philosophical as it is physical. Does observation create reality, or does it merely reveal what was already there? The answer forces us to confront the very nature of existence and our role within it as observers. This mystery of measurement is not some abstract curiosity. It is the fundamental schism between the quantum world and the world we experience, a gap that remains the most contentious and unresolved issue in all of physics. And just as we grapple with forces that seem to defy detection on the quantum scale, we once found an anomaly on a cosmic one, a tiny, unexplained push acting on our spacecraft deep in the void. Even the most meticulously planned missions can carry a ghost in the machine. For decades, as the Pioneer 10 and 11 spacecraft sailed into the dark beyond our solar system, NASA scientists noticed something was subtly wrong. Their speed was dropping by a fraction of a millimeter per second more than expected, an almost imperceptible but persistent deceleration pulling them back toward the Sun. This tiny, unaccounted-for drag became known as the Pioneer Anomaly, a whisper of a mystery in the vast silence of space. For years, it fueled speculation about exotic new physics, perhaps a sign of unseen dark matter halos or even a flaw in our understanding of gravity itself. The tireless work of scientists like Slava Turishev at NAS, a jet propulsion laboratory, eventually traced most of the effect to a surprisingly mundane source: the gentle but constant push of thermal radiation, as heat from the spacecraft's nuclear power units leaked away asymmetrically, acting like a tiny brake. Yet, even after painstakingly reconstructing the missions and accounting for this thermal recoil, a sliver of the anomaly stubbornly remained, a ghost that refused to be fully exorcised. This is not an isolated case. A similar and still unexplained phenomenon is the flyby anomaly, where spacecraft like Galileo and Rosetta have experienced tiny, unexpected gains in speed during gravitational slingshot maneuvers around Earth, as if the planet itself gave them an extra, invisible kick. These minute discrepancies force a humbling lesson that our mastery of physics is tested not only in the grand cataclysms of the cosmos but in the quiet, accumulating drift of a probe on a billion-mile journey. They remind us that the map of known physics is not yet complete, and that the blank spaces might be filled with subtle gravitational effects we have not even begun to account for. Could it be that dark matter interacts in ways we have not predicted, or that our equations of gravity require a tiny modification over immense distances? The Pioneer Anomaly, largely solved but never fully closed, stands as a testament to precision and patience, teaching us that the universe reveals its secrets slowly, and that even the smallest deviation can point toward a much larger truth. Deep in the cosmos, A single millisecond blast releases as much energy as our Sun emits in 80 years. These are fast radio bursts, or FRB, the 17th riddle etched into the fabric of reality. Discovered by accident in 2007 in archived data by astronomer Duncan Lorimer, these pulses are incredibly brief, vanishing almost as soon as they appear, yet they travel billions of light years to reach our telescopes. Some burst once and are never heard from again. Others, perplexingly, repeat their deafening cosmic shout on unpredictable schedules. Their origins are completely unknown, making them one of the most tantalizing mysteries in modern astronomy. The leading natural suspect is a magnetar, a type of neutron star with an unimaginably powerful magnetic field. The theory suggests that a starquake on the magnetar's surface, a sudden rearrangement of its crust, could unleash a catastrophic blast of radio waves. Another compelling idea points to the violent merger of two neutron stars, or a neutron star and a black hole. A collision so energetic it could power these immense signals. The challenge is that the bursts we detect are so intense and so fast that whatever creates them must be an engine of almost unimaginable power and precision. The repeating bursts add another layer of depth to the mystery. FRB 1211-2, for instance, was tracked back to a small, turbulent dwarf galaxy 3 billion light-years away. Its home appears to be a region of intense magnetic activity, further fueling the Matter-Antimatter hypothesis. Yet, the irregular pattern of its repetitions defies easy explanation. Could these bursts be focused by natural cosmic lenses? Some theorists propose that dense clouds of plasma between galaxies might act like a magnifying glass, focusing a weaker signal into the overpowering flash we detect. This very property makes FRB's potential tools, cosmic probes that can be used to map the otherwise invisible matter scattered throughout the vast voids between galaxies. As the radio waves travel across the universe, they are stretched and dispersed by free electrons, and by measuring this dispersion, astronomers can literally weigh the missing matter of the cosmos. But the extreme nature of these signals inevitably leads to a more speculative question. Could FRBs be artificial in origin? Could they be the leakage from unimaginably powerful transmitters, or perhaps even propulsion beams for light sails on an interstellar scale, as proposed by some scientists? While there is no evidence to support this, the possibility remains a tantalizing, if remote, thought. Are we listening to the natural death cries of collapsing stars, or to something else entirely? This cosmic enigma pushes the boundaries of known physics and forces us to wonder what other extraordinary transmissions might be hidden in the radio silence, waiting for the right moment to be heard. A single, deafening shout in the cosmic silence, never to be repeated. On August 15, 1977, the Big Ear Radio Telescope at Ohio State University recorded a signal so powerful and so perfect that astronomer Jerry Amon circled it on the printout and simply wrote, "Wow." Next to the data, it was a narrowband radio signal, exactly the kind predicted for an artificial, interstellar transmission, and it originated from the direction of the constellation Sagittarius. For 72 glorious seconds, it blared with an intensity 30 times louder than the background noise of deep space, and then it vanished. Despite decades of relentless searching by countless projects, including the massive SETI at Home initiative that harnessed millions of personal computers, nothing like it has ever been heard again. The signal's frequency was tuned to 1420 MHz, a number with profound significance. This is the microwave emission line of neutral hydrogen, the most common element in the universe. Any technologically advanced civilization would know this is a natural channel, a universal watering hole where anyone might be listening. It is the perfect frequency for saying, "We are here." So what was it? The leading natural explanations all fall short. Could it have been a comet? The specific frequencies comets emit do not match the WOW signal's profile. Was it a reflection of a human transmission bouncing off space debris? The signal's characteristics and the rotation of the Earth make that virtually impossible. The signal was not tracked moving across the sky like a satellite would. It appeared, held its strength, and then disappeared as the telescope moved on, which is exactly how a distant, fixed source would behave. This singular event stands as a monument to both hope and frustration in the search for cosmic company. It is the ultimate cosmic coquette, a one-time only performance that fuels our deepest wonder. Was it a fleeting hello from a distant star system, a message sent out eons ago that we happened to catch for one brief minute? Or was it a completely natural but unknown astrophysical event? A strange star that burped in a way we have never seen before or since. The wow signal refuses to yield its secret, a permanent enigma that reminds us the universe is still capable of genuine surprise. It is a siren song that continues to pull us toward the stars, searching for an answer to its solitary, unanswered call. This search for cosmic connection extends beyond signals to the very forces that shape the cosmos, including a magnetism that seems to permeate the void itself. Magnetic fields weave through the vast emptiness between galaxies, a hidden architecture sculpting the flow of matter and energy across the cosmos. These are not the simple fields of a bar magnet, but immense, organized structures that span hundreds of thousands of light years. They guide the birth of stars, channel cosmic rays, and leave their ghostly signature on the light that travels for eons to reach our telescopes. Yet their origin is the 19th riddle, a profound mystery. How did these powerful fields emerge from the primordial fire of the Big Bang, a state thought to be perfectly smooth and symmetric? Astrophysicist Ethan Siegel captures the puzzle perfectly, noting that magnetic fields are everywhere, but we do not know how they got there. The leading theories are as elegant as they are speculative. Perhaps they were born from quantum fluctuations in the very first instance of the universe, tiny seeds of magnetism inflated to cosmic size during the period of rapid expansion. Or maybe they were generated later by a cosmic battery effect, where the motion of ionized gas across the faint gradient of a gravitational field generated a weak electric current, which in turn created a magnetic field. Once these seed fields existed, the dynamo effect could take over. The churning motions of plasma within galaxies, much like the spinning molten iron in Earth's core, could have amplified these weak fields into the powerful ones we observe today. But here is the catch. We now detect magnetic fields even in the near-perfect voids between galaxy clusters, vast deserts of space with very little matter to drive a dynamo. This observation challenges our models to their core. How did magnetism get there? To even see these fields, astronomers rely on two brilliant tricks. Faraday rotation measures how a magnetic field twists the polarization of light as it travels through space, while synchrotron radiation is the telltale glow emitted by electrons spiraling at near light speed around magnetic field lines. These are the tools that reveal the invisible, so we are left with a reflective question. Do these pervasive magnetic fields hold a frozen record of the universe's infancy, a relic from a time before the first stars? If so, deciphering their origin could provide a direct window into the forces that shape the cosmos from its very first moments. This search for cosmic genesis pushes our instruments to their limits, demanding that we find ways to test the most profound theories, not just in the vastness of space, but in the controlled confines of a laboratory. Even our most powerful particle smashers are like firecrackers compared to the energies needed to crack the universe's deepest code. The 20th riddle asks how we can possibly test the theories of quantum gravity, which live at a scale so small it is almost abstract, the Planck length. This is a distance a billionth of a trillionth of a trillionth the size of a single atom. To probe this realm directly, we would need a particle accelerator larger than our entire solar system. Since that is impossible, scientists must become cosmic detectives, searching for subtle clues left behind in the fabric of reality. As physicist Lee Smolin has argued, we desperately need observational clues to guide us, a fingerprint of the quantum world on the cosmic stage. One promising avenue is the study of gravitational waves. When two black holes collide, they send ripples through spacetime that we can now detect. By analyzing the precise shape of these ripples, especially the faint after vibrations called the ringdown, we might spot deviations from Einstein's predictions, tiny signs that spacetime itself has a discrete quantum structure. Another method involves the very nature of light. According to some theories, the quantum foam of spacetime should make the vacuum act like a subtle froth, which could slightly scatter light waves traveling over billions of years. By studying the arrival times of photons from distant gamma-ray bursts or pulsars, astronomers are hunting for this blurring effect, a potential signature that empty space is not smooth after all. Precision tests of Lorentz invariance are another crucial frontier. This principle, a cornerstone of relativity, states that the laws of physics are the same for all observers, regardless of their speed or direction. But some quantum gravity models predict that at the tiniest scales, this symmetry might break down. Exquisitely sensitive experiments with atomic clocks or lasers are constantly checking for any drift or directional dependence in the fundamental constants, any crack in the foundation of physics. Even quantum entanglement itself could be a tool. The way entangled particles correlate might be influenced by the granular nature of spacetime at the Planck scale, offering a way to use a tabletop experiment to probe the architecture of the cosmos. The dream, of course, is a future observatory that could see the universe's first moments, a time when quantum gravity ruled supreme. This pushes us to ask a humbling question. Will we ever directly observe the quantum grain of spacetime, or are we forever destined to infer its existence from the faintest of cosmic whispers? This riddle challenges not just our technology, but the very limits of human ingenuity and experimentation. It suggests that the final answer may not come from a single instrument, but from a convergence of evidence, piecing together a puzzle whose final picture reveals that our three-dimensional reality might be nothing more than a projection. The universe might be a hologram, a magnificent illusion projected from a flat, two-dimensional surface at the very edge of everything we can see. This is the 21st riddle, the holographic principle, a radical idea born from the fiery paradoxes of black hole thermodynamics. It suggests that all the information needed to describe a three-dimensional volume of space, every star, every planet, and every one of us, is actually encoded on its two-dimensional boundary, like a cosmic fingerprint. Physicist Leonard Susskind captured this mind-bending concept perfectly when he said the three-dimensional world is an illusion. The most concrete evidence for this comes from the study of black holes. Stephen Hawking showed that a black hole's entropy, which is a measure of its hidden information, is not proportional to its volume as you might expect. Instead, it is proportional to the area of its event horizon, its two-dimensional surface. This area law hints that the true degrees of freedom of any region of space might live on its surface, not within it. The principle finds its strongest mathematical footing in something called the AD/CFT correspondence, a profound duality discovered in string theory. It demonstrates that a theory of gravity operating in a volume of space is completely equivalent to a quantum field theory living on its boundary without gravity. They are two different descriptions of the same reality. One is a hologram of the other. Applying this specific correspondence to our actual universe is highly speculative, as our cosmos is not shaped like the anti-de Sitter space the model requires. Yet, the core idea is so compelling that many physicists believe some form of holography must be fundamental to nature. If this is true, the implications are staggering. It could provide the key to resolving the black hole information paradox, suggesting that information swallowed by a black hole is never truly lost inside, but is instead smeared and preserved on its event horizon, like data on a vast celestial hard drive. It redefines the nature of spacetime itself, suggesting that the smooth, continuous fabric we experience is not fundamental, but emerges from a vast network of quantum information entangled on a distant surface. This forces us to ask a truly profound question. Is our rich, three-dimensional experience of life, the feeling of depth and solidity, just a magnificent projection, a surface code playing out on the cosmological horizon? Are we, in a very real sense, living inside a cosmic simulation? This rethinking of dimensionality itself leads us to a puzzle that is not about the grand architecture of the cosmos, but about a tiny, unstable particle behaving in a way that defies our best models. A tiny, unstable particle is wobbling in a way it should not, and its strange dance could shatter our understanding of the subatomic world. This is the 22nd riddle, the mystery of the Muon G2 anomaly. Muons are the heavier, unstable cousins of electrons, and like all particles with spin, they act like tiny magnets. The strength of this magnetism is called the G-factor. The standard model of particle physics, our most successful theory, can predict this number with breathtaking precision, but there is a problem. The muon's measured magnetic moment, its G-factor, is slightly stronger than the theory says it should be. This is not a small error. It is a persistent, statistically significant deviation that has haunted physicists for decades. Recent experiments at Fermilab have confirmed this discrepancy with even greater certainty, sending a jolt of excitement through the global physics community. As expert Graziano Venenzini puts it, this could be the first crack in the standard model. The wobble is caused by the muon's interaction with the quantum foam. As it moves, it constantly emits and reabsorbs virtual particles, a cloud of fleeting existence that subtly enhances its magnetic strength. The standard model accounts for all known particles in this cloud. The fact that the prediction is wrong strongly suggests there is something else in that cloud, a particle or force we have not yet discovered. The leading candidates are the stuff of theoretical dreams. It could be evidence for supersymmetry, a theory that predicts a shadow partner for every known particle. Or perhaps it is a hint of dark photons, carriers of a hidden force that interacts with the dark sector of the universe. Another possibility lies in the calculations themselves, specifically a complex component known as hadronic vacuum polarization. This refers to how the muon interacts with the seething sea of virtual quarks and gluons, and our understanding of this process might be incomplete. But if the anomaly holds, it points squarely to new physics. It is like carefully calculating the weight of a sealed box, only to find it is ever so slightly heavier when placed on a scale. That extra weight must be something inside you did not account for. For particle physicists, this tiny wobble is a beacon, a flickering signpost pointing toward a vast and hidden landscape of particles and forces beyond our current imagination. What invisible dancers are sharing the quantum stage with the muon, subtly tugging on its spin? The answer could ignite a revolution as profound as the discovery of the Higgs boson, or even more so, finally revealing what lies beyond the standard model's brilliant but incomplete horizon. This search for cosmic completeness extends even to the very elements forged in the first moments of creation, where another stubborn discrepancy awaits. The universe's first few minutes were a frantic forge, a nuclear firestorm that created the first atomic nuclei. The predictions for how much hydrogen and helium should have been made are spectacularly accurate, a triumph for the Big Bang model. But there is a stubborn outlier, a nagging inconsistency that has persisted for decades. The predicted amount of lithium-7 is 3 times greater than what we actually observe in the oldest stars. This is the cosmological lithium problem, a small but profound crack in our story of creation. Cosmologist Brian Fields called lithium a persistent thorn in our side for good reason. These ancient stars act as cosmic time capsules, their atmospheres preserving the pristine chemical composition of the early universe. When we analyze their light, the lithium signature is consistently and puzzlingly low. The discrepancy is too large to ignore. It suggests that our understanding of those first explosive moments is incomplete. Perhaps our models of the nuclear reactions themselves are wrong. The cross-sections, which measure the probability of particles interacting, might need revision. Scientists are running sophisticated laboratory experiments to test these rates with ever greater precision. Or maybe the solution is more exotic. Could unknown particles have been present, subtly altering the nuclear processes? Theorists have proposed that actions, the same hypothetical particles candidates for dark matter, could have drained energy from the primordial plasma, cooling it just enough to change the amount of lithium produced. If the solution involves new physics, it forces us to reconsider the entire environment of the Big Bang. Was something else at play in the universe's first moments, a shadow process we have not yet accounted for? This tiny deficit of an element challenges the very details of our cosmic origin story, reminding us that even our most successful theories can hide deep and lingering questions. And if the initial conditions of the universe hold such secrets, perhaps its overall geometry does too, pointing toward a strange and unexpected alignment that some have dramatically called the axis of evil. Our most fundamental assumption about the cosmos is that it has no center and no edge, that it looks the same in every direction. This cosmological principle is the bedrock of modern cosmology, the reason we can extrapolate from our tiny corner of the universe to the whole. But the oldest light we can see, the cosmic microwave background, whispers that this might be wrong. There is a strange alignment in its patterns, a preferred direction that has been dubbed with dramatic flair, the axis of evil. This is the 24th riddle, a ghost in the machine of creation that refuses to be exorcised. When we look at the map of the CMB, the afterglow of the Big Bang, we expect to see a random, isotropic distribution of hot and cold spots. Instead, the fluctuations show a surprising degree of alignment with the plane of our own solar system. It is as if the universe has a faint but undeniable tilt, and we are somehow sitting along its axis. This is not just a statistical fluke. Data from the Planck satellite, our most precise map of the early universe, confirms that these anomalies persist. They are real features in the data, not artifacts of the instrument. As cosmologist Kate Land admits, it keeps us up at night. So what are we seeing? The most conservative explanation is that we are fooling ourselves. Perhaps there is some unknown foreground contamination, some subtle emission from within our own galaxy or even our solar system that is muddying the pristine signal from the edge of time. We have meticulously subtracted everything we can think of, from dust to synchrotron radiation, and the alignment remains. Could it be something more profound? Some theorists suggest it might be a hint about the overall shape, or topology, of the universe. If space is not infinite but finite and connected in a strange way, like a video game where going off one edge brings you back to the other, it could create patterns that look like alignments from our particular vantage point. Others point to those primordial magnetic fields, suggesting their large-scale structure could have imprinted a direction onto the fabric of space-time itself. The most radical possibility is that the cosmological principle is simply incorrect, that the universe is not isotropic after all, and that we occupy a special, if not central, place within a larger structure that has a preferred orientation. This idea is so unsettling that physicists resist it fiercely, and for good reason. It would force a complete rewrite of our cosmic story. This enigma is a profound reminder that our foundational assumptions are always provisional. The universe is under no obligation to conform to our desire for simplicity and symmetry. The axis of evil is a cold splash of cosmic water on our faces, a signal that the deepest mysteries often lie not in what we have yet to discover, but in the data we already have that refuses to make sense. It forces a humbling question. Are we seeing a flaw in our instruments, a flaw in our theories, or the first glimpse of a universe far stranger than we ever imagined? This challenge to fundamental physics is not confined to the grand cosmic scale, but also appears in a small, seemingly impossible engine tested right here on Earth. A rocket engine that needs no fuel sounds like pure science fiction, a fantasy of free energy that defies one of physics' most sacred laws. Yet for years, a small, oddly shaped metal chamber called the M-drive claimed to do exactly that, creating thrust without expelling any propellant whatsoever. This is the 25th riddle, a controversy that pits tantalizing experimental results against the unshakable bedrock of conservation of momentum. The principle is simple, a law as fundamental as gravity itself. For every action, there must be an equal and opposite reaction. A rocket pushes exhaust backward to move forward. The M-drive, its proponents claimed, somehow broke this rule. It was a closed system that appeared to push against itself. Inside a tapered copper cavity, microwaves would bounce around, and the subtle difference in radiation pressure between the wide and narrow ends was said to generate a tiny but measurable net thrust. When NASA Advanced Propulsion Lab, EagleWorks, reported a small positive effect in a vacuum, the story exploded. Had we stumbled upon a way to reach the stars without carrying immense tanks of fuel? Physicist Mike McCullough proposed a speculative theory, suggesting the drive might be interacting with the quantum vacuum, pushing against a sea of virtual particles that flicker in and out of existence. But the mainstream physics community remained deeply, and rightly, skeptical. The measured thrust was minuscule, often on the same order of magnitude as the experimental noise. Meticulous follow-up investigations almost always pointed to prosaic explanations. Thermal expansion of the device as it heated up could mimic thrust. The Earth's magnetic field could interact with current flowing in the electronics. When other teams built more precise experiments, like the one at Dresden University that used a super-sensitive pendulum in a near-perfect vacuum, the thrust signal vanished. The effect was almost certainly an artifact of measurement, a subtle error born from our desire to find a breakthrough. And yet, the idea persists in alternative science circles, a testament to our deepest yearning for a revolution in how we traverse the cosmos. It forces a reflective, almost philosophical question. Are conservation laws absolute? Or could there be hidden loopholes in the fabric of reality that allow for such miracles? The M-drive controversy, though likely closed, serves as a crucial lesson in scientific rigor, a reminder that extraordinary claims require not just extraordinary evidence, but a willingness to let go of a beautiful dream when the data simply is not there. It brings us to the edge of our understanding of motion and energy, and leaves us staring into the final, most fundamental mystery of all, the true nature of the void from which everything emerged. Even the void itself is a lie. The final and perhaps most profound riddle asks us to confront the nature of nothingness itself. We look at the empty space between stars and call it a vacuum, believing it to be a true void. But quantum physics reveals this is an illusion. What we perceive as nothing is actually a seething, dynamic sea of potential. Virtual particles, pairs of matter and antimatter, constantly blink into and out of existence, borrowing energy from the universe for a fleeting moment before annihilating each other and paying the debt back. This is the zero-point energy of the vacuum, a background hum of activity that never ceases. This is not just empty space. It is a medium filled with quantum fields that permeate all of reality. The Higgs field, for instance, gives particles their mass by interacting with them as they move through this cosmic molasses. This dynamic void is directly linked to the greatest failure in physics, the cosmological constant problem. where the theoretical energy of this vacuum is astronomically larger than what we observe. The philosopher Jim Holt framed the ultimate question that arises from this: why is there something rather than nothing? The answer might be that true nothingness, absolute non-existence, is inherently unstable. Some theories suggest that the universe itself could have spontaneously erupted from a random quantum fluctuation in this primordial nothing, a bubble of space-time that nucleated out of the void. In this view, our entire cosmos could be the result of the vacuum's innate restlessness. The multiverse concept takes this further, proposing that our universe is just one bubble in a frothing, eternal meta-universe where new worlds are constantly being born from nothing. This leads to a mind-bending reflection: could absolute nothingness ever truly exist? Or is the very concept a philosophical illusion, a state that is so unstable it inevitably gives birth to something? This final riddle ties every other mystery together, from dark energy to the Big Bang, forcing us to question the very ground of being. It asks not just how the universe works, but why it is here at all. We have journeyed through 26 enigmas, from the ghostly pull of dark matter to the spooky connection of entanglement, from the fine-tuning of constants to the mystery of our own consciousness. Each one is a thread in the magnificent tapestry of reality, a puzzle that pushes the limits of science and philosophy. They remind us that the universe is far stranger and more wonderful than we ever imagined, and that the greatest adventure lies not in having all the answers, but in daring to ask the questions. These 26 cosmic puzzles are not isolated islands of ignorance, but a single, interwoven web of mystery. Tug on one thread, and the entire tapestry of reality shudders. The hunt for dark matter is inseparable from the nature of gravity itself, which is the very problem quantum gravity seeks to solve. The fine-tuning of the universe for life is intimately connected to the possibility of a multiverse, a concept born from the mathematics of inflation. And the bizarre rules of the quantum realm, where particles exist in multiple states at once, may hold the key to the deepest mystery of all, the nature of consciousness. As Carl Sagan so beautifully observed somewhere, something incredible is waiting to be known. The incredible truth is that these somethings are all connected. A breakthrough in one area does not just solve a single riddle. It sends shockwaves through our entire understanding of the cosmos. Discovering the true identity of dark matter could instantly resolve the missing mass problem in galaxies and reshape our models of cosmic evolution. A complete theory of quantum gravity would not only explain the center of a black hole, but could also reveal the origin of the Big Bang and the fundamental structure of space-time. This interconnectedness is why the scientific quest is so powerfully unified. It demands that particle physicists talk to cosmologists, that neurologists collaborate with quantum theorists. The tools we build to probe one mystery often become the keys to unlocking another. The James Webb Space Telescope, for instance, is not just looking at the earliest galaxies. It is peering back in time to observe the formation of the first stars, potentially revealing the conditions for life's building blocks, while simultaneously measuring the expansion rate of the universe with unprecedented accuracy, thereby constraining the nature of dark energy. Every new dataset has the potential to address multiple enigmas at once. This grand synthesis leads to a final, humbling question. When these solutions finally come, not as isolated facts but as a new, unified framework for understanding existence, how will it transform human civilization? Will it give us mastery over energy and space-time? Will it reveal our true place in a cosmos far grander than we ever dreamed? Or will it simply instill in us a deeper, more profound wonder for the incredible reality we are so privileged to inhabit? The pursuit is not a collection of separate paths, but a single journey toward a brighter, more complete dawn of understanding. These 26 riddles form a single, magnificent web of cosmic mystery. Each question, from the ghostly pull of dark matter to the quantum enigma of measurement, represents humanity's unending thirst to understand the reality we inhabit. They are not abstract academic puzzles. They are the very forces that shape our technology, redefine our philosophy, and will ultimately chart our future among the stars. The physicist Neil deGrasse Tyson offers a humbling reminder, noting that the universe is under no obligation to make sense to you. And yet, it is our relentless curiosity, our refusal to accept the surface of things, that drives all progress. This journey invites you to reflect. How do these profound mysteries inspire you? Do they compel you to look up at a starry night sky with a deeper sense of wonder, to question the very nature of the world around you? If this exploration has ignited your curiosity, please like this video and subscribe for more deep dives into the universe's greatest secrets. Share your thoughts in the comments below. Which of these 26 riddles captivates you the most? Thank you for watching, and never stop wondering.